Welcome to the Explainer. Today, we are diving into a classic coding puzzle that, it seems super simple on the surface, but it's got this surprisingly elegant solution. Our mission? We're going to be counting battleships on a board. But there's a twist.
So let's just get right into it. This puzzle seems pretty straightforward, but there's a clever little constraint that's going to force us to think outside the box as we scan the grid.
The task sounds simple enough, right? Just look at a grid like this one and tell me, how many battleships do you actually see?
All right, here is our game board. It's just a simple matrix where an X marks a piece of a battleship and a dot, well, that's just empty water. Go on, take a good look. How many ships do you think are there?
Okay, before you lock in your answer, there are two really important rules you need to know. They're simple, but honestly, they are the key to cracking this whole thing.
First up, ships are just straight lines of X's, either going across or up and down. And second, and this part is absolutely crucial, ships never, ever touch each other. They're always separated by at least one little square of water, not even at the corners.
Now, if you just jumped right in and started counting, you might have fallen into the classic trap of this puzzle, and that is double counting. You know, a really simple but totally flawed approach would be to just scan the grid, top to bottom, and every single time we see an X, we add 1 to our ship count. I mean, it seems logical, right? But it's going to lead you straight to the wrong answer.
So, if we use that flawed logic on our board, we'd count 4 X's and get an answer of 4. But why is that wrong? Well, it's because we're counting every piece of a ship, not the ship itself.
And this is where the puzzle gets really fun. The source material hits us with a follow-up challenge. Can you solve it in a single pass over the board, using basically no extra memory and without changing the board at all? That O1 memory constraint, that is the real kicker. Think of it like this. You're not allowed to use a notepad. You can't just create a second grid to mark off the ships you've already counted. Nope. You have to solve it in real time with only the information that's right in front of you.
So how in the world do we solve this? Well, the solution is just incredibly elegant. It all relies on a single, really clever insight about how these ships are built.
Here's the trick. We need to stop thinking about counting the whole ship. Instead, we're going to focus on counting just one unique part of every single ship. And for this, we're going to call it the head.
So what exactly is a head? Simple. We're going to define it as the topmost, leftmost X of any given battleship. So if a cell has an X, but the cell right above it and the cell to its left are both empty, we've found ourselves a head.
And this right here is why this works so perfectly. Every single ship on that board, I don't care if it's 1 square long or 5, horizontal or vertical, every ship will have exactly 1 top left corner. So by only counting those, we're guaranteed to count each ship exactly once. It's brilliant.
Okay, let's actually apply this to our board and see this algorithm do its thing. We're just going to scan it cell by cell, looking only for those heads.
We're starting at the very first cell, position 0, 0. And hey, it's an X. So we check, is there anything above it? Nope. Anything to the left? Nope. That fits our definition perfectly. It's a head. So our count is now 1.
We'll keep on scanning until we hit the next X over at position 03. And again, we run the check. Anything above? No. To the left? No. Both are empty. That means we've found another head. Our count is now 2.
Okay, now for the really interesting part. On the next row down, we find another X at position 1, 3. So let's apply our rule.
So, is there an X to its left? No. But, and this is the key, is there an X directly above it? Yes, there is. So this fails our test. It is not a head, it's just another piece of a ship we've already found. So we ignore it. Our count stays at 2.
And we do the exact same thing for that last X on the board. We see it also has an X above it, so we ignore that one too. After scanning the entire grid, we land on our final and correct answer, 2 battleships.
So you see, this top left head strategy isn't just correct, it's also incredibly efficient, and it manages to meet all those tough constraints the puzzle threw at us.
I mean, just look at this. We checked every single box. We only went through the grid once, we didn't use any extra memory to keep track of stuff, and we didn't have to change the board one bit. It's just a clean, elegant win. The big takeaway here, the thing to really remember, is that this is a super powerful problem-solving technique for pretty much any kind of grid puzzle. Instead of trying to track these big, complex objects, see if you can find a single, unique property, some kind of anchor point that you can count instead.
And that leaves us with a final thought to chew on. Where else could this strategy of finding a unique anchor point totally simplify a problem that seems really complex on the surface? What other puzzles could be unlocked with this exact